Welcome to the first presentation in Unit 8. It's titled It's a Slinky. It says every wave, regardless of how high and how forceful its crest, must eventually collapse within itself. It's a quote by Stefan Zweig. Okay, so let's take a look at our learning goals. Our learning goals for this particular presentation are number one, that you be able to differentiate between a transverse and a longitudinal wave. So that's going to be an example of using vocabulary. Next, we say we want to identify the major vocabulary terms associated with waves. There's a lot of vocabulary in this particular unit, and we want to be able to predict the result of interference between two waves. So, what we already know that energy is conserved. That's one of the hallmarks that we've talked about since Unit 5. Energy is always conserved in a closed system. We also know that heat can be transferred by waves, and that's something we looked at in Unit 7. We called it infrared radiation at that point, but we also called it a wave. We also know that the electromagnetic spectrum gives us a lot of information about the universe. Now, that's from middle school, but it's something that you should know, that you can look at light waves and radio waves and those sorts of things. Now, what we learned in the lab. We learned that waves can occupy the same space at the same time. We call that wave superposition. The fact that you can have these two waves right here occupy this same space at the same time, resulting in a new wave. We call that wave superposition. We also learned that transverse and longitudinal waves have different properties. Okay, we also learned that the velocity of a wave depends on the medium in which it travels. Whenever you pulled the Slinky more, the wave traveled a little bit faster than whenever it was a loose wave. So the first thing we need to talk about in terms of vocabulary is something called simple harmonic motion. Simple harmonic motion is basically repetitive motion. So it's something that happens over and over again. Now, two of the main examples are whenever you have a pendulum, which is something that swings back and forth. Okay, you usually see them in grandfather clocks. That's an example of simple harmonic motion. What it's doing is it's doing the same thing over and over and over again with regularity. Okay, it also means that the force is proportional to the displacement. So in other words, the further you get away from what we call the equilibrium position, the further you get away, the bigger the force is. So there's more force here than there is when it's right here. Okay, example of a mass on a spring is another example. And sometimes this is actually called a spring pendulum. This is called a swing pendulum. This spring pendulum is the same thing. As you stretch the Slinky out, or as you stretch the spring out, there's more force, so it snaps back. So these are examples of simple harmonic motion. Well, another example of simple harmonic motion is a wave. Now, waves are traveling energy, and it's really important that you make that distinction. Whenever you have a wave in the ocean, the wave itself does not consist of water. Now, the wave does displace the water. So the water is here, and as the wave travels in it, it makes the water go up and down. And I know that's kind of an interesting distinction, but the wave itself is not the water. The wave itself is the energy that's traveling through the water. Because of this property, because the wave is energy, that means that you can have two waves occupy the same space at the same time, which is what we call superposition. Okay, that does not work for matter. If you try and have like your hand and the desk occupy the same space at the same time, it's not going to work. I think we have little finger issues, but whenever you have to try and occupy the same space at the same time, it won't work. Okay, you're either going to put a hole in the desk or you're going to hurt your hand as you try and break the desk. It's just not going to work. So, waves. Waves are emitted equally in all directions. So whenever you look at the sun, you can kind of see that. You can see the light being emitted in a circular pattern. It's not really a circular pattern. It's a circular pattern from where you view it. It's actually a spherical pattern because it's emitting it in all directions. So it's kind of hard to draw a sphere three-dimensionally. But realize the light is emitted in all directions. And that's true for all waves. Whenever you have a sound, okay, a sound is an example of a wave. It's emitted in all three dimensions in this spherical pattern. Now, these waves will continue forever unless they are dampened. Now, by dampening, what I mean is they actually start to get smaller. So some of their energy goes away. And you can see that if you're ever really close to a bright light, okay, and you go to that bright light and you go further away, it's nowhere near as bright because the energy has been dampened. Okay, it's been spread out. Same thing with sound waves. When you get further away from a source of a sound, it gets quieter because the energy has been dampened a little bit. So waves travel in a straight line. Okay, so unless you have something that we'll talk about later called refraction, okay, we're going to assume that waves travel in a straight line. So that means if I have a wave here and I can hear it, the reason why I can hear it is because that wave traveled in a straight line. And I know what you're thinking. You just said it's emitted in a circular pattern. Yes, what you do have is you have constant waves at every direction. So you have constant waves being emitted in every direction, but they all travel in a straight line. Because they all travel in the straight line, speed is the same thing as velocity for waves because they're going in the same direction. So the first type of wave we have is what's called a transverse wave. Now a transverse wave is one in which the oscillation of a particle is perpendicular to the direction of the motion. So this wave is moving, it's moving from left to right. The wave is moving as it goes across this way, like an ocean wave. The problem with this is if you were to look at an individual particle, so just one little particle, all that particle does is move up and down. It doesn't move left or right, it only moves up and down. That's the hallmark of what we call a transverse wave. So let's kind of dissect the definition a little bit. The oscillation. Oscillation means back and forth movement, so it's going this way and this way. In this case, the oscillation is up and down, so that's not a correct way to draw the oscillation. The oscillation is up and down. Okay, is perpendicular. Perpendicular means at a right angle to. So if you have the oscillation going this way, and you have the wave moving this way, it forms a right angle. So the oscillation is perpendicular to the direction of the wave's motion. Okay. Some examples of transverse waves are lights and waves on a string. Okay. So let's look at some of the definitions that define a transverse wave. The first thing that you have is the period. Now the period is defined as the time it takes to reach an identical point of the wave. Okay. You can only get a period graphically if it's a time versus displacement or amplitude graph. That's the only way it will actually work, is if time is here. If you do have time on the graph, you can pick any two identical points on the graph. So for example, if you were to look at the first one, I can look at this first peak. If I were to look at that first peak and then now the second peak, those are identical points on the same or on the waves. So because of this, this would represent the period or the time that it takes to get to identical parts of the wave. You should be able to do this for any point on the wave, not just the peaks and the troughs. So for example, if I gave you this point right here, you should be able to tell me where it's an identical point on the wave. Now a lot of people will say this, and that's incorrect, that's wrong. Okay, the reason why is when I'm here, I am at this same point, but I'm moving upwards. I'm in the crest part of the wave. When I get here, I'm moving down to the trough part of the wave. So even though it's the same position, it's not the same point of the wave. In order for it to be the same point of the wave, you have to be at the same amplitude, okay, which we'll talk about in a second, the same height, but you also have to be moving in the same direction. So this right here would be one complete wave. The time to go from here to here would be the period. Now the frequency is the exact inverse of the period. Okay, the frequency is the number of wave cycles per second. So if I were to give you something like this and say, hey, there's this many cycles in 1 second, you could tell me the frequency is 1, 2, and a half. So you'd say the frequency is 2.5 because there's 2.5 waves in 1 second. Now frequency and period are inverse to one another. The longer a period is, the shorter the frequency. Now, waves are generally expressed as mathematically as a sine or a cosine graph. If you were to put y equals sine x into a graphing calculator, you would get something that looks like this. Now, there are some factors that you can do to manipulate it to look like any other sort of sine wave, but that's something that you'll have to do in another math class. So a couple of more definitions. Okay, there's lots of definitions in this one. The crest is an easy one. It's the highest point on a wave. That right there represents the crest. The trough is the lowest point on the wave. Okay, a lot of times we think of the crest as the highest point or the maximum energy. Okay, it turns out that's generally a good way of thinking of it, and you can think of the trough as the lowest point of energy or the minimum energy. A wavelength is very, very similar to the period, at least graphically. Okay, the wavelength is defined as how long or how far it is between identical points of successive waves. So remember on the period how we said, okay, from here to here, the time it takes to go from there to there is the period. Well, if you were to look at it and instead of having time, if you had distance, this would actually give you the wavelength. That's the length between those two identical points. Now the last definition that we have is the media. and the media is what the wave is actually traveling in. Okay? Oh, I was wrong. We actually have a couple more definitions. As energy increases, the amplitude increases. Now, what amplitude is it's the size of the wave. So how far does it come from this middle line? This middle line is what we call the equilibrium line. If it's the equilibrium line, how far you extend from that equilibrium line represents the amplitude. Now, you can measure the amplitude going from the highest point to the middle or the lowest point to the middle. Both of these are the amplitude. Okay, notice how it is not from the top to the bottom. That's the most common mistake. That is not the amplitude. The amplitude is from the crest to the equilibrium line or the trough to the equilibrium line. Amplitude is generally related to energy, so whenever you think of it as a sound, a louder sound will have a higher amplitude. Whenever you think of it as light, a brighter light will have a higher amplitude. Okay, you have a pulse wave, and what a pulse wave is it's a single part of a transverse wave. Now, this is what you did in the lab. You create a single pulse. In other words, there's a crest, but there's not a trough. And what this is, it's not a continuous thing. It's a one-time deal, and it's used to study the behavior of waves at a boundary. So a boundary is what happens when it hits a surface. Now, you guys did this in the lab. You said, okay, there's somebody else holding the Slinky here. What happened when the wave hit? And you saw that it reflected back. Okay, so let's look at some examples. The first one says, what direction will the wave particles oscillate? So what you can see is that the velocity of the wave is moving from left to right. You can recognize this shape as being a transverse wave. Because it's a transverse wave, you know the oscillation has to be perpendicular to the direction of motion. Here's the direction of motion. What's perpendicular to that would be this right here. This right here is the only one that's perpendicular to the direction of motion, and therefore it is our answer. Okay, the next one says a pendulum swings such that it travels 35 centimeters from the equilibrium point. Sketch a graph of displacement versus time and label the following. So the first thing that we want to do is we want to draw our wave. We have an equilibrium line. That's our 0 point. Okay. Now we know it's going to go all the way up and then all the way down and then all the way up and then all the way down and then all the way up. And what we're going to stop there, and what we did is we drew two complete wavelengths. So if you see, I start right here. There's the end of the first wavelength. There's the end of the second wavelength. So I've drawn two wavelengths. Now it says I need to label these things. The crest. The crest represents the point of highest energy. The crest is actually going to be at 35 centimeters because 35 centimeters is the farthest from the equilibrium point. And that's when it's going to swing all the way out here. Okay. Now it's going to go all the way back to the middle. Then it's going to go to the trough. The trough is going to be at minus 35 centimeters because it's going to swing the exact same amount on the opposite side. So this makes us have our crest and our trough. The amplitude would be the distance from the equilibrium line to the crest or the distance from the equilibrium line to the trough. Notice how they're the same value. 35 to 0, 0 to negative 35. They're the exact same magnitude as far as number is concerned. Okay, the equilibrium line is this line right in the middle, and that represents our 0, and it's also this dashed line in our original picture. And then the last thing we need to have is period. In order to have the period on this particular graph, I need to label this graph. It needs to be a time versus amplitude graph. And then I can pick any 2 points on successive waves. Since I've already marked these two, I'm going to use this point and this point. If I look at the time between those 2 points, that would represent the period. Notice how it doesn't ask me for wavelength. And the reason why it doesn't ask me for wavelength is I would have to relabel the graph as something different. You can either get wavelength or period from a graph, but not both. Next, we have a longitudinal wave. A longitudinal wave is one in which particles oscillate in the same direction as the motion of a wave, or sometimes it's called, instead of same direction, it's called parallel. Parallel is a better word for it. So we have a wave that's moving from left to right. As that wave moves from left to right, if you were to look at an individual particle, what it does is it oscillates back and forth in that same direction, parallel. So if we dissect our definition again, it says particles oscillate, which means move back and forth, in the same direction as the motion of the wave, or parallel to the motion of the wave. So a wave moves this way, particles oscillate back and forth parallel to it. Now, sometimes longitudinal waves are referred to as compression waves. Compression waves are the same thing. They oscillate in the same direction as the motion. There's a couple of different vocabulary terms associated with a longitudinal or a compression wave. Instead of there being a crest or a trough, we actually call it a compression. It's the point where it's squeezed together. That's the equivalent, the rough equivalent of a crest. It's the point of maximum intensity. Then what you have is called the rarefaction. The rarefaction is the point where it's stretched out the most. So the rarefaction is the point of minimum energy, and it's considered to be a trough. Now it says label parts A and B. How many wavelengths are there in D, and what is the amplitude of the wave? So the first thing that you want to do is you want to look at this thing and you say, okay, A is clearly a compression. It's a point where it's squeezed together, so that's going to be my compression. It's going to be my point of maximum energy. B is going to be my trough, and it's going to be my point of minimum energy. If you were to look at D, realize that, okay, we got to figure out what's going on with D. D would represent, I have a compression and a rarefaction, a compression and a rarefaction, and a compression. Well, if I told you I had a wave that was a crest and a trough, you would say that's one complete wave. If you had another crest and a trough, that would be two complete waves. If we added another crest, that would be 2.5 waves. Well, we have the equivalent here. I have a compression and a rarefaction. That's one wavelength. I have a compression and a rarefaction. That's my second wavelength. And I have a compression, which gives me my half wavelength. So there are 2.5 wavelengths in this particular drawing. The last thing it says, what is the amplitude of the wave? Now, a lot of people will automatically go to C because they say C is how high up and how far down it goes. But remember, an amplitude represents how far it is from the equilibrium position. Remember, this represents the crest, and this represents the trough. So if you were to take the distance from A to B and divide it by 2, that would represent the amplitude of the wave. Now, why divide by 2? Let's go ahead and clear a little bit of space out and let's draw it again. If you were to take the equivalent transverse wave, you have a crest and you have a trough and you have the equilibrium line. Remember, this was 35 in our example and this was minus 35. If you were to look at the distance between the two, the distance was 70. 70 divided by 2 gave us our 35, which was our definition of the amplitude. It works the same way for a longitudinal wave. You take the compression, which is the crest, you take the trough, which is the rarefaction, add them up, divide by 2, and you would get your amplitude. It says earthquakes contain both transverse and longitudinal waves. Only one of these waves causes destruction. Using the properties of waves, identify the type of wave, and justify your answer using the clear method. So the first thing you have to do is realize, okay, I have an earthquake. Here's the surface of the earth, and I have to ask myself, does the earth moving parallel to a wave cause damage, or does the earth moving up and down relative to a wave cause damage? Now you can see from this particular picture, the earth has moved up and down, and that's what actually causes the cracks and causes all the damage in the buildings and so forth. So it's actually the transverse wave is going to be the answer. So if I want to formulate this in the clear method, what I'm going to say is the clear method is I'm going to say transverse wave. Okay, so now I have to have some sort of evidence. So my evidence is going to be earthquakes are both, I'm going to shorten them just for space sake, T and L waves, transverse and longitudinal waves. So now my reasoning why is that transverse waves oscillate perpendicular to the wave, making the surface, and I'm going to say buckle, which means move up and down. So this is an example of using the idea of the properties of waves to explain something that you probably know a little bit about, that are earthquakes. Next, we have what's called wave interference. Wave interference happens when two waves occupy the same space at the same time. Sometimes we call it the superposition of the waves. What happens is instantaneously two waves become one. So if you have a wave, we'll just call it a pulse wave, and you have another pulse wave, for an instant that they occupy this same space at the same time, there is not two different waves. For a brief instant, there is only one wave, and you get the superposition of that wave, which results in something like that, which is what you saw in the lab. Okay? Superposition results in waves that can increase in amplitude. If the waves increase in amplitude, what you have is what is called constructive interference. An example of that is this. If I have a wave here, and then we'll change the color, and we'll do another wave right on top of it, what happens is these waves are occupying the same space at the same time. The superposition is always additive. So the resulting wave of adding these two together is going to be one massive wave. Okay, you're going to take these two and add them together. So say each one was 1, the resultant of the new wave is going to be 2. You always add them together. Now, if you were to look at it, that's called constructive interference because the wave increases in amplitude. You can also have what we call destructive interference. Destructive interference happens when you have something that looks like this. You have a pulse wave there, and you have a pulse wave here. And if you look, a crest overlaps with a trough. Well, if you were to look at the numbers, this would be something like -1, and this would be something like +1. Remember, superposition is always additive. So if you add these two together, what you get is 0. And what happens is it temporarily destroys the wave. So the wave temporarily doesn't exist. And then the waves continue along their original path because they all travel a straight line velocity. So in this one it says, when these two waves meet at point P, what will the resultant amplitude be? If you were to look, you have an amplitude of A, and you have an amplitude of -A. I know it's minus because it's underneath the x-axis. So when I take A and I add -A, I get 0. So the resultant amplitude is 0, or there is no wave. The last one we have is a student is investigating the possibility of generating true noise cancellation headphones. Explain what would be necessary to truly cancel out a sound. Well, if you think of a sound as a wave, in order to truly cancel out that sound, what you need to do is you need to produce the exact opposite of this sound. So you'd have to produce something that looks like this. And when you do that, interference will occur. Interference would result in no wave. If there's no wave, there's no amplitude, there's no volume. If there's no volume, there's no sound.